Hello, this is Rashmika Ramana. I'm going to discuss about the Lab 3 program, Part 1, that is Universal Shift Register with the D flip-flop and 4 is to 1 mux. So after verifying the Universal Shift Register on the Nexus board and its functionality, the further task which was given was to create a test bench and the source code for a D flip-flop. This is the D flip-flop code without the reset button, and this is going to be the respective D flip-flop test bench. So in the first part, we had to verify the D flip-flop and the marks. So in the first part, so that is with the D flip-flop, as a D flip-flop is nothing but whatever input we give, the output will be the same. So here I'm going to consider the D, that is the input, clock signal, output, and the NOT of the output. So what? So since the input is one in the first clock cycle, and one more important point is that it's going to be a positive edge triggered clock. For every positive edge triggered clock, there's going to be an output. So with the input D is equal to 1 and also clock is equal to 1, Q will always be 1 as it's a D flip flop, uh, and the NOT operation of Q is going to be 0. Similarly, if the D input is 0 and the clock will be 1, the output will be 0 and the NOT of the output will be 1. So this is the functionality that was supposed to be verified, and this is the D flip flop. Further, I'm going to explain the functionality of the 4 is to 1 mux. So in the 4 is to 1 mux, we were supposed to write the code, and also we were supposed to verify the functionality as we did for the D flip flop. And I'm going to show the same for the 4 is to 1 mux. Firstly, we will change the directory for the USR, since all the code, all the files is going to be in it, and create a new library called work. Similarly, execute using the TCL code. At this point, we're going to use the multiplexer, that is 4 is to 1 multiplexer, which was supposed to be coded and verified. Changing the time scale for 429 seconds as it was given in the TCL, as written in the TCL. So considering the 4 is to 1 marks, so this is going to be the 4 is to 1 marks that I've coded, and it's going to have 4-bit input, 2-bit select lines, and 1-bit output. So the ideology is that whatever the select line, so the output is going to select the particular input. Suppose if the select line is 00, the output should be I naught, and if the select line is 01, the output should be I1. If the select line is 11, then the output should be I0. Whatever the other input is going to be, then output should be 0. For the same, I have coded even the test bench, giving all possible input combinations. So now we would verify the same using the Modelsim. So here we can see that when I0 is, okay, first we're going to put this in the terminal. So when the select line is 00, and also I0 is 0, I1 is 1, I2 is 1, and I3 is 1. So since the select line is 00, it has to choose, the output should be 0 because it is going to choose the I0. So the respective output is 0. And when the input is 0, 1, 0, 0, so that is IN is 1. Similarly, the select line is 0, 1. the output is going to select the I1 and the I1 input is 1. So the output is going to be 1. Same way when the input is going to be 1101, so that is when the I2 is going to be 0, and when the select line is 1 0, it has to choose the input 2. So the output water and the output is going to be same as the input 2. So the input 2 is 0 and the output is also going to be 0. Similarly, when it is going to be 1 1, the input of I3 is 1, so the output is going to be 1. So like this, we can verify, through this we can verify the functionality of the 4:1 multiplex. Thank you. Hello everyone. In this video, I'm going to discuss about the Lab 3 Part 2 of 8-bit universal shift register using the D flip-flop and the 4:1 mux. So according to the task given, we were supposed to include the D flip-flop with the reset signal. So coding the same in the behavioral model with the reset signal on. So the ideology is that when the reset signal is on, the output and the input should be 0, since the input will be 0 and the output of the D flip-flop will be equal to the input. So we can justify the same in the functionality that has been given. So when the on the every positive edge of the clock, when the reset is 0 and the D, and at every positive edge of the clock, we can see that the input is 0 and the output is also going to be 0. So when the reset is 1, so the input should be 0 and the output will be 0, while the QN, so that is the NOT of output, will be 1. The same, when the reset is 0 on every positive edge of the clock, the D input is 0 right now, so the Q will be 0. And when the D input is 1, when the reset is 0, the Q will be 1 while the QN will be 0. So we can see the same in all the clock cycle. So we've seen when the reset is 1, the input going back to 0. When the reset is 0, it's going on every positive edge of the clock. It has to take the value of 1, and the output will also be 1, and the QN will be 0. So this can be performed, this was performed using the reset. Well, when the reset will be on, so everything, the input will go back to 0. That is the lower input. Thank you. Hello everyone. So in this video, I'm going to discuss about the shift register, that is 8-bit, and the functionality of the 8-bit shift register using D flip-flop and mux. So in the previous video, we've seen that the universal shift register was performed using the behavioral code, that is using the select lines and just the behavioral code. And the mux and the D flip-flop was individually performed um, and simulated. That was in the previous video. So in this video, I'm going to show how the D flip-flop and the mux component was instantiated in the USR source code. So in this video, I've declared the component of the mux, the component of the D flip-flop, and I've configured both by giving the internal signal and connecting the port map so that the universal shift register performs using the mux and the D flip-flop. So the structural code and the behavioral code has been implied in the same code that was given before when it had just behavioral. Now the add-on was the structural description. So since we have configured both the behavior, both the mux and the D flip-flop, we were supposed to do the same in the test bench using the configuration column. So after verifying both the D flip-flop and the mux, so the respective output that we've got is, so first of all, that it's been verified that it's successfully done. And later, so when the output was, as you can see that the expected output and the data out has been given. So the ideology is that when the select line is 0, 0, it the output is going to be the same as the previous input. That is, it's going to be in the whole condition. So in the first select line, that is 1, 1, output is going to be the input. So we can see that the expected output and the data output has been matched to the input. So this is the condition for the select line 1, 1. So when the select line is 0, 0, it has to hold the same value which is there. So the expected and the data out is similar, and it is same as the previous output. The previous output was the 1, and the present output is also 1. So we can see that on every positive edge of the clock, there has been changes. And when the select line is 1, 0, we can see that it is performing left shift. So it was 1, and the 0 has been moved towards the left. 1 has been moved towards the left. We can see that the uh, left operation has been performed, and the expected and the data output has been matched. You can see how the left shift operation has been happening. So since it is 0, 0, again it has to hold the value, and it's going to hold until the next operation. The next operation is 1, 1, 1, 0, and we can still see that the left shift operation is being performed successfully. So when it is 0, 1, when it is 0, 1, right shift should happen. So we can see that the right that the 1 has been shifted towards the right. So this was the previous output in the low edge of the clock. In the positive edge of the clock, you can see that the bit has been right shifted. So it will continue unless there is going to be the next one. On every positive edge of the clock, so when there is 1, 1, the select line is 1, 1. So the output is going to be same as the input. And you can see the same. And this is going to be in hold condition, going to continue the same. So 1, 0, again there has to be a left shift. You can see that the left shift just performed. 0, 1, and there's going to be right shift. 1, 0, left shift again, and 1, 1. The output should be equal to the input. So this was the functionality of the universal shift register with the mux and the D flip-flop. So this was successfully performed till the 400 nanoseconds. Thank you.